Here we go, onward with more graphs of equations. Here we see the equation y equals x cubed, and its graph looks like this. So whatever x is, y is that number to the third power. That number times itself times itself. So like if x is -2, y would be -2 times -2 times -2, which is -8. If x is -1, y is -1. If x is +1, y is +1. If x is +2, y is +8. Notice something here. When x was negative, y was negative. And when x was positive, y was positive, but it was just the positive or the negative of the same thing. So here's an example of a graph that is symmetric with respect to the origin. It has origin symmetry. The graph does pass right through the origin. In one direction it goes up like this into quadrant 1, and then it goes down like this into quadrant 3. So it's sort of the same thing off in the opposite direction. If we took the whole thing and just rotated it through 180 degrees, it would match up with what we have now. So for every point with a positive x and a positive y, we have a corresponding x with a negative x and a corresponding point with a negative x and a negative y. 1, 1, -1, -1. 2, 8, -2, -8. 0.5, 0.125, -0.5, -0.125. And look at, if we play around with the equation and apply that algebraic test for symmetry with respect to the origin, if I replace x and x and y at the same time with -x and -y, -x cubed, that's a negative times a negative times a negative, it remains negative. So -x cubed is -x cubed. Negative times negative times negative is negative. X times x times x is x cubed. And then we have -y equals -x cubed, but we can divide both sides of that by -1, and we get the same equation we started with, y equals x cubed. So it passes that test for being symmetric with respect to the origin. Okay, now what about intercepts? The y-intercept would be where the graph crosses the y-axis. And here that happens right here at the origin, at the point 0, 0. And that same point is also the x-intercept. It crosses the x-axis and the y-axis at the same time. Look at this equation. X squared plus y squared equals 25. And the graph of that equation is a circle. Points on the circle include x could be 0 and y could be +5. X could be 0 and y could be -5. Either way, 0 squared plus either positive or -5 squared would be 25. X could be 5 and y could be 0. X could be -5 and y could be 0. And then we have all sorts of other points on the circle. We have the points where x is 3 and y is -4. Where x is 3 and y is +4. Where x is 4 and y is 3. Where x is 1, y is a little bit less than 5. It's about 4.899. Or we also got a point down here where x is +1 and y is -4.899. What kinds of symmetry do you see? Well, actually, this has all three of these kinds of symmetry. It's symmetric with respect to the y-axis, and also with respect to the x-axis, and also with respect to the origin. It's got two y-intercepts, one up here at 0, 5, and one down here at 0, -5. And it has two x-intercepts. Can you see what those are? Yeah, 5, 0, and -5, 0. And we will be coming back later in this section to talk more about circles and their equations. Stay tuned. But now, how about this equation? This graph is something called the Folium of Descartes, and the equation here is x cubed plus y cubed equals 3xy. Does it have any of the kinds of symmetry we talked about? Well, not any of these. It's not symmetric with respect to the y-axis or the x-axis or the origin. Now, there's other kinds of symmetry you could talk about. If we drew a diagonal line right along here, it would be symmetric with respect to that line. That's just not one of the three kinds of symmetry we were specifically looking for here. And what about intercepts? Well, there's only one point where it touches either of the axes. It touches both of them at the same time right there at the origin. So the y-intercept and the x-intercept are both 0, 0. How about this equation? You can keep this one in mind for Valentine's Day. X squared plus y squared minus 1, and then the whole thing cubed equals x squared times y cubed. The graph of this equation is this heart shape. What symmetry do you see? Well, it is symmetric with respect to the y-axis. And I could have predicted that just from looking at the equation, because anywhere there's an x in the equation, it's being squared. So if I replaced x with negative x, the squaring would kill off the negativeness, and it would be equivalent to the equation we have now. What about intercepts? Well, I see two y-intercepts, 0, 1, and 0, negative 1. If you wanted to check, if you plug 0 in for x and either 1 or negative 1 in for y, the two sides should be equal. And I see two x-intercepts, 1, 0, and negative 1, 0. And now for something really elaborate, the Batman equation. So this big, ugly, complicated equation right here has a graph that looks like the Batman symbol. So all the points on this graph have x and y coordinates that satisfy this equation. Now you may be wondering, how on earth could anybody have come up with that? An equation that complicated where the graph turns out to be this Batman symbol. Well, I'm not going to explain it, but I will put a couple of links on Canvas that you can check out. There's a video that talks about this equation. There's a website that it kind of explains how somebody actually came up with this and figured out that this is the formula that you need to graph to get this. But I will point out that the graph is symmetric with respect to the y-axis. And if you look at the equation, everywhere there's an x in the equation, it's either inside absolute value bars, or it's being squared, or there's a couple places where if you multiplied it out, then you'd have just an x squared. But if you really know what you're looking for, you could have at least predicted that the graph of this equation was going to be something that was symmetric with respect to the y-axis. Okay, so I mentioned that we were going to talk about circles towards the end of this section. So I'm going to end this video here and come back in the next video and talk about how what an equation for a circle looks like and how you can tell what circle you're dealing with from the equation, or vice versa. See you then.